So let's have a look. The rate at which the range changes is what we mean by radial velocity. And so we need the component here. Now that side of the triangle is V, the angle in there is phi. So this side of the triangle here is going to be V times the cosine of that angle, V cos phi. So that's the radial velocity. And then we just plug that in. 400 meters per second times cos of 45 degrees is 282.8 meters per second, which we round off to say 283 meters per second. So every second, the object is 283 meters further away from the radar detector than it started. What's happening with the angle? Well, we saw how these things are related. V equals R omega. We just go back up. This V here is the tangential velocity. So tangential velocity is the radius times the rate of change of the angle. So V trans rate of change and radius times the rate of change of the angle. So the rate of change of the angle theta dot is going to be the tangential velocity, so tangential speed, because we're only interested in the magnitude here, divided by the radius. So that's, what is the tangential component? It's here. Remember, we're splitting our velocity into a radial component and a tangential component, and that is going to be V sine theta, sine phi, I'm sorry, where phi is the angle between the velocity and the radius vector. So we just plug that in, V sine phi divided by the range, 400 sine 45 degrees divided by 3,600, and we get a number there, 0.0786, and that will be in the natural units, which it'll be in units of radians per second. I'm not that familiar myself with what a radian per second means, so we just convert that to degrees per second, which we can easily do, multiply by 180 divided by pi, because remember, every radian is 180 on pi degrees. Let me just write that down. People that have... So we just multiply this answer by 180 over pi, and we get 4.5 degrees per second. What is 4.5 degrees? Well, the full moon is almost exactly half a degree. So this will be going across your line of sight, and in 1 second it will travel the equivalent of 9 full moons. So it's changing, not super rapidly, but quite rapidly. So we've now calculated R dot and theta dot. We now then have to think about the acceleration. Let's go up again. Okay, so the acceleration is in the direction of the velocity vector. So on my sketch, I've put in a red arrow to show the direction of the acceleration. And we can go through exactly the same procedure as before. So the green arrow there is the direction of the radius, and the red arrow is the direction of the acceleration, and we can split that into a radial component and a transverse component. And what the radial component is, that's increasing the range in that direction, and the tangential acceleration is going to be affecting the angle with respect to the horizontal. So the transverse component changes theta. So R double dot is the rate of change of the range. That should be A. Whoops, excuse me. That there's a mistake here. That is A. Cos phi. That'll be the tangential component, A cos phi. Because that side, we want this side of the triangle. This side is A. Angle in there is phi. So this side of the triangle is going to be A times cos phi. So that's going to be 3 times cos 45 degrees. Multiply that out, we get 2.1 meters per second squared. In teams where this problem is set, the radial acceleration is given and it's just the wrong value. It should be 2.1 meters per second. If we want to have a look at the rate at which the angle is changing here, that's due completely to the tangential acceleration up there. And we saw that the tangential acceleration is the radius times the angular acceleration. Easy. So A equals R alpha or R theta double dot, same difference. So the angular acceleration is going to be the translational acceleration divided by the radius of curvature. That'll be A. Let's see, it's this side of the triangle here. That side is A. This angle in here is phi. So this side of the triangle, the magnitude of the transverse acceleration is going to be A sine theta. So we just plug that in. A sine phi, I'm sorry, not theta, A sine phi divided by the radius of curvature, 3 times sine 45 degrees divided by 3,600. We get that angle acceleration there in units of radians per second squared, and you could convert that to degrees per second squared if you so wished, using our simple conversion factor of 1 radian is 180 on pi degrees. Okay, so let me just go through this one again because I suspect it's going to there's quite a lot sort of going on here. So we wanted to know the rate at which the range is changing and the range is accelerating, and how the angle is changing with respect to time and what the rate of change of the angular velocity is. That'd be theta double dot. So what we did was we recognized if we have the velocity, we can split it into components. One component is radial, that changes the range, and another component, the transverse component, that changes the angle. And because it's at right angles to the radius velocity, so it's at right angles to the radius, this component is not going to change the range. And it's easy to work out what each of those components are. The radial component, that's V up there, that's phi in there. So this is going to be, this side of the triangle will be hypotenuse times the cosine, and this side of the triangle will be the hypotenuse V times the sine. And the radial velocity is changing the range, so we just plug it in. The transverse velocity is R omega. What has happened to this thing? Or if you like, R theta dot, same thing, because omega and theta dot, they're exactly the same thing. So we can calculate then the rate at which the angle is changing. It'll be the transverse speed divided by the radius. Plug it in, and we've got an answer. And that answer, it's in radians per second, but it's worth converting to degrees per second just to make it easier to do it. Okay, how are we going for time? Acceleration, we mark it in, split it into components in exactly the same way as before, and calculate the rate at which the range is accelerating. It's 2.1 meters per second squared outwards. And we calculate the rate at which the angle is accelerating. And that turns out to be this value here. Okay, motion in one direction. Yeah, we've got about another 10, we'll have to go about 10 minutes over time, I'm afraid. So let's suppose we're describing motion in one dimension. We have to do that with respect to some frame of reference. So for example, let's suppose you're on one of those travelators that you often find at the airport. And you're walking along the travelator at, say, 5 kilometers per hour. And let's suppose the travelator is moving at 4 kilometers per hour. How fast are you moving over the ground? Well, you're going at 5 kilometers with respect to the travelator is going at 4, so the combined motion over the ground would be 5 plus 4, 9 meters per second. It's really very simple. So here we've got the speed with respect to the a moving frame V, and we've got a stationary frame, say the ground there. If we want to know what the speed measured in the moving frame is when we compare it to the speed over the ground, easy, just add the two together. So the speed of this thing with respect to our stationary frame here will be the speed with respect to the moving frame plus the speed of the moving frame with respect to the ground over there. Usually we pick the ground as the sort of stationary frame. Just add the relative motions together. So if anybody has to leave for another class, could you please make sure you do the quiz, which is in Teams, within the next half hour or so. We'll be using that to record attendance. Okay, so just back to here, relative motion in 2 dimensions. Let's suppose we have a plane flying. So it's moving through the air, but the air may be moving with respect to the ground. And we want to calculate how fast is the plane moving with respect to the ground. And that's very simple. We just take the velocity of the plane with respect to the air, and then we add the velocity of the air with respect to the ground, and the sum of those two will be the velocity of the plane with respect to the ground. So here we've got a case where there's east, there's north. The plane heads due north. It just keeps a compass course north. But the air is moving in this direction here. It's actually got a fairly significant westerly component and a little southerly component as well. The southerly component is going to act to slow the speed of the plane, and the westerly component basically just makes it move west. How do we find out what the actual speed over the ground is? We just add the 2 velocity vectors together. The speed of the plane with respect to the ground will be the speed of the plane with respect to the air plus the velocity of the plane with respect to the ground will be the velocity of the plane with respect to the air, plus the velocity of the air with respect to the ground. Just add them up as vectors, and it's we're done. Let's have a look at an example. So let's consider a small rowing boat attempting to row across a river. The rower powers the rowboat at a speed of 0.75 meters per second through the water, and the water is not stationary. It's flowing east at a speed of 1.2 meters per second. So we can ask, what is the velocity of the boat over the ground? So let's take our little sketch, and we just have to add the velocity of the boat. It says it's crossing. It didn't actually say what the direction was, but it's clearly north. Okay, so that way's east. There's the velocity of the water going east. The velocity of the boat is right angles to that. And we just add them as vectors. So we want to add a vector in that direction plus a vector horizontally. And that's easy to do with Pythagoras. We just take the sums of the squares and then take a square root. So that'll be 0.75 squared. And this side is 1.2 squared. And add those squares, take a square root, you get 1.415 meters per second. Data's only to 2 figures, so the answer will only be more or less to 2 figures too. We also need the angle, and that's easy to calculate. So that's this side of the triangle on that side of the triangle. And this side of the triangle is just velocity of the boat over, with respect to the water, and that one was water over the ground. And so we just take the tangent of this side, which is 0.75 meters per second. That one was 1.2. That'll be tan theta. So we take an inverse tangent and we end up with 32 degrees. So the velocity of the boat over the ground is 1.4 meters per second, and we have to specify the angle as well. It's going to be 32 degrees north of east, and we're done. Okay, so here's a little summary of what we have done. We looked at vectors. We know how to calculate position, the change in position. That's the displacement. The velocity, that's the rate of change of displacement. And if we're working in unit vectors, it'd just be dx dt times the unit vector for the x direction, which is I, plus the y velocity, that'll be dy dt times the unit vector j. And we can do the same for the acceleration. And it's very important to remember the velocity is always tangential to the path. And for relative motion, velocity of something with respect to A is the velocity it starts with respect to B plus the velocity of B with respect to A. Those problems take a little bit of practice, so I suggest you have a look at some of the problems in OpenStax or Wiley. For projectile motion, we have no acceleration in the horizontal direction and acceleration of minus g in the y direction. It's assuming we take upwards as positive. So just the x coordinate, whatever we start with, plus the x velocity, and that's just going to be the initial speed times cosine of the initial angle times t, and y, this initial position, this is going to be the initial y velocity times t minus a half gt squared. And we can calculate these speeds. Remember, the x speed doesn't change at all because there is no horizontal acceleration. The y speed, we have an acceleration of minus g, so we can calculate it this way. there's the range. And remember, it depends on basically sine 2 theta and the square of the initial speed. So if you double the projectile velocity initially, it's going to go 4 times as fast. And for all the problems we will be looking at, air resistance can be ignored. And that maximum range is going to occur where the sine 2 theta is a maximum, so that's where theta is 45 degrees. So a launch angle of 45 degrees gives you the maximum range. And for radial motion, we saw the angular displacement was the arc travelled divided by the radius of curvature, measuring in radians, our natural unit. And we saw how to calculate the centripetal acceleration. That's the acceleration pointing into the center, v squared on r. Period is the time it takes for one complete revolution, 2 pi r divided by the speed. So that's, yeah. And omega, change in angle with respect to time. The tangential speed, r times omega. And the tangential acceleration, r times alpha, or r theta dot. Okay, so next week we're going to look at forces, dynamics. Up until now, we've just been considering pure motion. Kinematics is the jargon term. So next week we start looking at dynamics, forces. That'll enable us to look at Newton's laws of motion and Newtonian mechanics. The pages that you should read before next Monday, we'll be meeting at 2 o'clock on Monday. So there was some question of that. Yeah, it's 2 p.m. So chapter 4, pages 133 to 156. And chapter 5, there's 2 sections there to have a look at, 176 to 180 and 210 to 214. There's a PDF up on UTS online, which has all the slides of today. I will update it. I saw that there were 1 or 2 little mistakes. That'll be done today. They're not very important. And I will try to get the slides up for next week. Probably will be Saturday, but if I can get it done by Friday up there, I will.
Hey, Jim.
Okay, well, thank you, sort of everybody. I know some people have got to go. Please don't forget to do the quiz. And if you could do that quiz in the next half hour, unless you've got a clash with another course, that would be very good. Where is the quiz? Yeah. The quiz is on Teams. Let me see if I can go through. And we have Microsoft Teams. So I'm just going to move that. Okay, so we go to Files. No. Teams. Tick. Physical modeling. We want the weeks. We need to get into the I can't see on my version. We should be able to pop up in general.
Isn't it in the class notebook?
Posts. We should end up with a little arrow over. There we go. Okay. Content library, weekly material. Okay, week 2. Week 2 new stuff. Inga. Taking its own sweet time.
Righto.
I think it's in the in lecture, which it's just taking its own time to load. Ah, let's see if that's.
Hi, Jim. Jim?
Okay, I don't know why that isn't loading, but that's where it
Jim?
should be. It was
there's-
there last time I looked. It's just a white page. It's not loading anything
His
at all.
name is James, not Jim.
James, there's nothing in that folder.
Okay. Hopefully it will be there in a
James,
minute
if you
or
look
two.
at if you look at week 3 in lecture, there's actually a quiz, but I don't think it's the one that you're talking about though. Look at the week 3 one in lecture.
It's week 2.
Yeah, but week 2 is
Right,
it's all
so
empty.
Teams is not accessing those things.
I think it is working. It's just taking a while. I opened it in the actual OneNote app, and it
Just
loaded up
restarting
after a while.
Teams.
Okay.
I did it. I sent it on the this. Ready? 3, 2, 1, go.
Is the quiz supposed to have 3 cars and a yellow
No,
background?
seems blank. Okay, guys. I think we'll leave it there. Thank you very much for your attendance.
So what's happening
And
now?
I'll speak to you again
There's
at
a
2
quiz
o'clock
in
on
chat.
Monday.
There's a link
Keep
in
well.
chat.
Wash your hands.
Is the quiz supposed to be you're driving
Chat
at
has
110
quiz.
kilometers an hour and stuff?
I think
Yo, Rip. Bro, this
And the ones I don't believe, they be a major majority. I wasn't always the stoic, guess it came with maturity. And I show you how I feel and you can show me it orally. Take it how you wanna take it, you can look at me horribly. They gon' make a story so and say I'm acting immorally. And my purpose on this earth won't let me follow authority. And some men in there